Remember that. Hands up who remembers that we proved this. How did we prove it? Well, if you start somewhere and you want to end up in the same place, the only way to navigate on this kind of graph is to go to the other side and then back and then to the other side and then back and then to the other side and back, because all edges are from one side to the other. So the only way to get back to the left side, if you start on the left side, is to have a 1, 2, 3, 4, 5, 6, 7, 8. So the only way to get back here is the even number of edges. That's the easy part. And in some of the sections that went very fast and some people maybe knew more about graphs, we actually proved the other way too, but not in all sections. So what's explicitly the other way? The other arrow means, I'm going to state this other arrow again in words. If graph G has all cycles even, then it's bipartite. That's the backwards implication. Again, the straightforward one, it's easy. It says, if it's bipartite, a cycle must be even, any cycle. That's okay. But the other way, here's a random graph G, and we know there's no odd cycle in it. All cycles are even. Why is it that's bipartite? So I'm going to do that proof here, but like any proof in class, the proof consists in what I write on the board and what I say in words. The technique of this proof is by coloring. It goes like this. Pick a vertex, some random vertex, color red. Or if you don't like red, let's call it, I'm going to keep red because it's a standard coloring schema, but red in my case, it's the same as left. I'm going to call it left. I'm going to call this side here left. I'm going to call this red. And this other side right, I'm going to call it blue. It's just a matter of notation, because it doesn't matter how you call those things. It's just a name for the set. If you call it red or left or white or the Virgil side, it doesn't matter. So coloring red it is a standard coloring schema, so then I will use that. I'm going to pick a vertex, color red. So this is my first vertex here. Let's call it V, V1. So I made this one red. And then what I do, I go from all the edges from this vertex, so I have 3 edges. So follow all edges incident in V1, that is this node here, and color the other edge end for this edge. So for those 3 edges, I get 3 ends here. Color the other ends blue. That is the right side. So now I left V1. I have here V2, V3, and V4. I declared those blue. And I keep repeating this schema. For the vertices I just colored at the previous step, for vertices colored at the previous step blue, so I'm not considering V1 anymore. I'm only looking at the vertices that I just colored blue. That's V2, V3, and V4 in here. I do the same. I repeat this step. Follow all edges. So from here I have no edge. From here I have no edge. But from here maybe I have 2 edges. Because these edges are going back, so I have some other vertices here. Follow all edges and color the other end back to red. So now I've got this V5, V6 here colored red. And then I keep repeating. For the nodes that just colored red, I look at all their edges and I color everything on the other side blue. And I keep doing this until something happens. So repeat. until the end of time. No, not the end of time. Until what? The end of time? No. Until, what are the possibilities here? How can this thing end? There's more than one possibility. There's several cases, and how can this end? Yes?
One possibility could be that all your vertices are either red or blue.
All vertices are?
Are either red or blue.
Okay, so one possibility for ending until what? So they say possibility one. All vertices colored red and blue, right? Nice and easy, no problem. In which case, I'm going to say what? If that worked out and I color vertices, what am I going to say? It's bipartite. Even more, I actually found the two sides. Which are the two sides? The red and the blue, right? So that implies bipartite. What else can happen? Yes?
You could go back. So let's say you're alternating between red and blue, and you run into a vertex that's already colored, but it's already, let's say it's already colored red, and it says to and based on the steps that you've taken, it says colored blue, then it's not bipartite.
So already color, say red, and I'm attempting to color again blue. So I have a vertex that has been color red, and by going back and forth, back and forth, back and forth, I get an edge back that says, you have to color this one blue now. In that case, I declare what? Not bipartite. In fact, what I just found is a what? A what? A cycle that is odd. I just found an odd cycle. So if my purpose was not bipartite, but find an odd cycle, somebody gives me a problem in CS 1800 exam. How do you find an odd cycle? That's how. Right. What can happen, another possibility,
you can't reach any more vertices.
Cannot, I want to say that right here, the last one, because I want another possibility in there. So he's saying, I cannot reach, I finish coloring by edges, but there is some other vertex. See, these sets are a little bigger. Right? So I do this coloring here, I'm done, everything is nice and smooth and fine, but there's some other vertices that I didn't get to because the graph is disconnected. Then what? If that's the case, there's no way this connected component here, it's not connected to the rest of the graph. So while there's edges left to right in the back component, down component, it's not reachable from where I started. So the connected, disconnected is the same principle like any other graph. Even if it's bipartite, it could be connected or could be disconnected. Is it clear what I'm doing? I'm drawing too many lines here. I make it confusing. Let's draw this picture nicer. I'm talking about a situation where this part is all connected and there is another part here that's all connected, but there's no connection between the parts. That can happen, right? Then what do I do?
Apply the algorithm to the other connection component.
Keep going, right? Just pick another vertex that was not colored before, make it red, and keep going from there. So cannot reach some vertex, restart procedure. And it's the same, keep going. The possibility I'm skipping here, that perhaps not obvious, I have the same like in here already color, but I'm attempting the same color. So it was color red, and my procedure said color it red. So already colored red. Red, attempt color red. So it was red, and now my procedure said color it red. What do I do then?
Choose another path.
Yes.
You found an even cycle.
Right, I found an even cycle, very good. And then what? About bipartite, what do I have to do? What do I have to do? If anything, yes.
You don't really know anything at that point, so you have to keep going.
Keep going. That's how I can, this is a very constructive proof, very computer scientist proof, in that it proves the theorem, but also give a constructive algorithm that you can write a program based on to detect bipartition, or odd cycles, or even cycles. It's not just an existential philosophical proof, it's actually giving you a method to find the thing. Right? Who's with me so far? Very good. So the coloring thing is a very powerful technique. These ideas with going through graph and color for various purposes. In this I keep track left versus right, but I could have a different purpose. For example, I want to keep track of what vertices are done, as in processed, what vertices are not yet detected, observed, and what vertices are in processing. If I have, say, some algorithm that traverses the graph. I want to keep track, and the coloring schemas are used a lot. So when you start thinking about algorithms, some of you already done that, some of you will study algorithms next year. The idea of coloring a node to indicate some status of it is quite powerful. And then depending on how the edges work out, you know, the colors might change, right? Every time I stop processing a node, I may decide to change its color from white to black or something. If you've seen algorithms like DFS or BFS, you've probably seen that they use some coloring schema to keep track of what happened. Now, if you haven't seen them, that's fine. You'll study them in the algorithms course. So that's my first interesting proof for today. Another thing that I've been looking at. Somebody can claim that? Another thing that I've been looking at, we've been talking about this Eulerian path. Eulerian cycles. I'm going to put path or cycles. The difference is path doesn't have to end where it started. Cycle has to end where it started. Okay? What was the central notion in the Eulerian paths of cycle? Yes, middle.
It hits every edge exactly once.
Pass through every edge once. It's nice to say sometimes exactly once. There's a philosophical argument, if I just say once, do I mean exactly once or at least once? And nobody can agree on that. So if you want to be sure, whoever reads your paper understand what you say, I would say be safe and say exactly when it's exactly and at least once when it's at least once, to not create confusion. Question?
The Eulerian cycles can't cross a specific node twice.
They can.
They can?
In fact, they did a lot. If you look at these examples we had before with the Kronisberg bridges.
In general, if you have a cycle...
We keep saying, you mean vertices.
Right, for vertices, yeah.
You can come, you say in, out, remember? And then there was another one, in, out. Clearly I'm crossing this more than once.
Sure.
So I can't step on edges more than once. I have to step on every edge twice. Edges were in that problem were what? The bridges. But the landmasses, which are the vertices, I could come on every landmass multiple times. So Eulerian cycle, you have to pass through all the edges exactly once. And if it's just path, it's the same thing, except it does not require to end where you start. And we already know what this comes down to, right? We've been talking about a few lectures about this.
Right.
What is the essential mathematical criteria to allow this to happen? Remember what it said? Where theorems back and forth, if this happens, that happens, and if that happens, this happens. What was that? The degree of most vertices have to be even. I hope you also remember the proofs. If there is an Eulerian cycle, degrees are even. And if the degrees are even, there is a way to find an Eulerian cycle. We found one cycle, and if that was not the whole graph, we say, okay, find another cycle with intersection points. And if that's still not the whole graph, find a third cycle. And then we say there is a way to join those cycles together to obtain an Eulerian cycle out of it. Hands up, who remembers that? All right? So we have to remember the results, of course, to use them, but also the proofs. Okay, so that's all good. I'm gonna make a variation of this problem. I'm gonna call it Hamiltonian cycle. Very simple variation. Pass through all exactly once. All vertices, right? So instead of requiring stepping on all edges exactly once, that is, I could go multiple times on vertices. Now I'm requiring all vertices exactly once. So just thinking out loud, can I step on an edge more than once if I want to step on all vertices exactly once? No, because to walk on an edge twice, you have to step on the end points of the edge more than once, and then that's not possible, right? So how does this stuff look like? Hamiltonian cycle. Is it always possible? Is it not sometimes possible, sometimes impossible? Yes?
Just a clarification, because it's a cycle, you will have to do the starting one.
In the ending, the same point, right? So that doesn't change path of cycle. This notion is the same like irregular graph. If it's a path, you have to have a path starting from somewhere, ending somewhere else, with the criteria once every vertex. If it's a cycle, it's a path once on every vertex. That's the Hamiltonian property, but it requires to go back to where you start.
So I have a clarification question. Is like a Valerian tour or Hamiltonian tour is the same as a cycle, right?
A tour, I think it's called the ones, yeah, there might be a cycle, a tour. They have different names. They call it paths, trails, tours. I think the tour means a cycle, as in you come back, but I'm not 100% sure, because it's more like a convention of names. I would like you to not use a lot of names for your own, because you get confused with so many names. Just say cycles versus paths. Or if you like cycles, tours versus trails. Oh, well, nobody knows what tour means, really, so that's a problem right there. Cycle, I think, is pretty clear. It has to come back where it started. So when is a graph having a Hamiltonian cycle? I mean, hold on, I'm gonna get back to it. When, here's a graph, right? I don't know, what did we have this graph before, right? Or what was it? Oh, we were drawing the triangle here with something, and here's a graph. Like, remember this graph before? You guys said there was a Eulerian cycle here, right? There was a way to start in a point. Actually, what's the degrees of this graph? All vertices. 2, 4, 2, 4, 2, 4, all even. According to the theorem, there must be an Eulerian cycle in it. And I think it's easy to find. How about the Hamiltonian cycle? Can you pass through all vertices exactly one and end up where you started? Okay, so let's see how that goes. A, B, C, D, E, F. How do I do it? Say, where do I start? A. Then go where? B. Then go where?
C, D, T,
Where?
E, F, F.
Very good. Not too hard. But the question stands just like in Eulerian cycles. When is this thing possible? And when it's not possible? Any idea? Yes.
The point you start with has to have a degree of at least 2.
To go in and out.
Yeah.
But that seems necessary, of course. However, I don't think it's at all sufficient.
Oh.
Right? So he's saying an obvious thing is like if you go out of this node, you have to come back in. That's fine, but that's very far away from saying that's sufficient to determine the cycle. Yes.
Is it impossible for the bridge?
For the
For Hamiltonian cycle?
Königsberg bridge, you mean?
No, like a bridge where there's sort of there's an additional component.
You took the bridge like we define a bridge in class, an edge, that's a bridge. So I think he means if you have a bridge in your graph, so you have a graph somehow, and there's connections here and there's connections here, but this is a bridge. A bridge means there's no other connection, right, from left to right. That's what a bridge is. So he's saying if you have an edge UV, you cannot have a Hamiltonian cycle. That's what you say? Is that true? Can I have a Hamiltonian cycle if I have a bridge? Yes or no? So I have a bridge. Your hypothesis here is no Hamiltonian cycle. I think the idea being you start somewhere, the cycle has to pass through all vertices. Every cycle can be rotated. Once I have a cycle, instead of starting in some point on the cycle, I can start somewhere else on the cycle and still follow the cycle. So if a cycle passes through U and all other vertices, one way it's going to reach to V, because it has to reach all vertices, right? So the only way to reach V is to pass this bridge. But now I'm in V side, I can't close the cycle. I think that's what the thinking here is, right? This is an extremely hard problem. Not hard for you, hard for everybody in the world. It's one of these problems that no one knows how to solve. Yet, maybe somebody soon will solve it. Yes, that's possible. But it's a problem that's extremely difficult. So people have attacked it in several ways.
Is the problem, how do you qualify a Hamiltonian cycle?
What property of the graph determines Hamiltonian cycles?
Yeah.
Yes or no? Is it a problem like something with degrees or connectivity or, how do you determine? In fact, in computer science, we take a math problem like this and we make it programmatic. It says, write a program that determines if a graph has a Hamiltonian cycle. So since there's no good math, no easy math like in here, because this math is very easy, it's very easy to write a program to determine an Eulerian cycle, right? What do you have to do? Check all the degrees, which is very easy to check from the adjacency matrix or from the adjacency list, right? Check the degrees. If they're all even, done. You don't actually have to find the cycle because there's a mathematical backend that says if all degrees are even, there is a cycle. So if there will be some property like this for Hamiltonian cycles that we can check very easily from the matrix, that would be great. We can write the program that way. Unfortunately, it's not. So when it's not, the only obvious solution for all problems is to try all possibilities, right? I mean, literally go through the graph, check all the possible cycles, try this edge, I'm here, go there, I'm here, go there. Okay, didn't go well, go back, try another edge. And then if I find a cycle that closes, I can check, is this cycle Hamiltonian? How do I check that? Passes through all vertices, right? And because there's no good math backend to this problem, the only way we know how to solve a problem like this is to literally try all possibilities and see if we find one that's good. In graphs, cycles can be a very large number. Even with a small graph, like 6 or 7 vertices, the number of cycles in it could be like in the thousands. So the cycles as a number can grow exponentially with the size of the graph. By the time you have 100 vertices, which is still a small graph, right? Think about Facebook. What's 100 vertices for Facebook? It's nothing. Think about Google. What's 100 web pages? It's nothing, right? Even 1,000 web pages. The number of cycles with 1,000 vertices could be an astronomical number. It's very difficult, even with a supercomputer, even with a farm of supercomputers, to try all possibilities if there are many. So this is that kind of problem that we don't have a good solution yet. We have solution for partial cases, and we have solutions for certain properties. We know how to prove some properties, and I want to prove one today. But it's not a general if and only if. This was a clear if and only if. Easy, back both ways. In here, what I want to prove, what I can prove, they're better results than the one I'm going to show you today, but they become very complicated, and no result is total. Like it's not a full characterization of how to find such cycle. The result I want to prove is this way. If property I'm going to list here, then there is Hamiltonian cycle. The property I'm going to list, if there's n vertices, that is size of V is n, and the degree of every x is at least n by 2, then there is a Hamiltonian cycle. All the theorems that ensure Hamiltonian cycles effectively state one property. You have to have enough edges. The property you're looking at for Hamiltonian cycles, it's effectively all these theorems. This is the simplest one, which took 100 years to prove. And there's more complicated ones that are really complicated. But all of them say the same thing. If you have enough edges, you can find the Hamiltonian cycle. The problem is what exactly is enough. This one says you have to have everybody connected to at least half of the rest. Right? So clearly that doesn't happen in Facebook, right? It's not like every user of Facebook is connected to half of Facebook users. But if you have this property, that's called the Dirac's theorem. So let me state this in English so you can see how this is not a total abstraction. This is not just some craziness that I come up with. It actually can happen in a very natural setting. So I'm going to restate this theorem with a simple analogy. So I have n people, and everyone knows. Knows means I'm acquainted to or I'm friend with, whatever you want to replace there, knows. N by 2 or more. And this relationship knows is reciprocal. What does reciprocal means? If I know you, you know me. And in graphs, that reciprocality means what? The graph is undirected. So I want to say there is a Hamiltonian cycle, but I'm not going to say it with the words Hamiltonian cycle. I'm going to say it, we can arrange those people at the table. So there is an arrangement at a round table such that everyone knows. Again, knows is the same relation that I had before. It's friends with or I'm acquainted with. Knows both neighbors. So an arrangement at such a table means this person here is connected to the two that he knows. So the reason I'm stating it's in English is because this might show up in a social setting where people have no idea what graphs are. You know, you have a party in computer science faculty department and everybody knows about, say, half of the faculty. That's quite common. You know, I probably know about half of the other faculty in the computer science department. And they have a big round table, you know, basically end of the year party. How can you put everyone at the table so they know the people next to them? It's not an uncommon problem that shows up all the time. How do you travel among cities that have roads between them? You know, same kind of thing. So this can easily pop up as a natural question and not as a purely abstract question. You're looking for this.
Not perfect.
All right? And now what I want to say is this property here in English the same mathematical property here? Am I stating the same thing? When I say everybody knows half of the people, is it effectively saying the degree of everyone is n by 2? How about this? Is this saying there's a Hamiltonian cycle? The arrangement of a table means if this is possible, everybody knows everybody. That means I have edges between the neighbors in the graph. And the fact that I put everyone at the table means these edges form a cycle which passes through all vertices exactly. So the arrangement at a table of those people, it's a Hamiltonian cycle if there is edges between every every one of them, right? So this arrangement is essentially the Hamiltonian cycle. Now this is not true the other way. If there is a Hamiltonian cycle, it doesn't mean everyone has to know half of the people. That's easy to prove by a counterexample. You draw a large cycle that's Hamiltonian, but everybody knows only, right, 2 people. So if I just draw a cycle like this as a graph, clearly that's a Hamiltonian cycle, but everyone has only degree 2. So this property goes one way, but not the other way. So how do we prove this? In the previous years, I stated this like before in a recitation or a problem, and I want to give people 3 days to solve it, and we concluded it's way too hard to solve it at home. So how do we prove this? And that was at the end of the course, when everybody was in December, you know, because presumably everybody knew more math, and now it's in the beginning of the course. So that's an additional wrinkle. We're going to have to use some notions that we don't know yet, but that's okay. We shouldn't be afraid of things we don't know. That's why we're here, to learn things, right? Like one of the things we don't know yet, I mean, I'm sure you know it. You just don't know the name. Pigeonhole Principle. How many people know what it is, Pigeonhole Principle? Very few people, but if I state it, I bet everyone knows what that is. The Pigeonhole Principle says there's 120 students in this class. Let's say 121 students. And there's 6 recitation sections. True, by the way. I have a lot of word disturbed because you guys have so many. The Pigeonhole Principle says if that's the case, at least one of the recitation sessions, the biggest one, must contain at least how many students? There's 121 total. They get distributed to those sessions somehow. There is no restriction for how people can be distributed. This principle says one section at least must be large enough. 21. Because it's very simple to show the thing. If all sessions would be 20 or less, the total would be just 120. Right? So again, Pigeonhole Principle, which we didn't study, we're going to study next week, which is still a little bit of advancement. If you have a big collection of items and you try to fit them into boxes or sessions or whatever you call them, there is at least one box that has to contain that many, because if all boxes are small, you can't get to the total. That's one thing that we're going to need here. So let's try to figure out this proof. Hopefully it doesn't take the whole day because I have a lot more to say, but number one that we want to say is a proof. First item of the day, that's very easy. G. So what's the hypothesis again? This is what I start with. I have size of V is n, and size of every degree is at least n by 2. That's what I know. That's what I start. And what I want to prove, I want to find a Hamiltonian cycle going through all vertices exactly once. So part number one is very easy. G must be connected. Such a graph that everybody has n by 2 connections cannot be disconnected. Such a graph cannot be, here's a component, here's another component. No connection between them. Why is that? Somebody else. Why can't I have 2 components with this property? Yes?
So if you put the 2 components, then even if you split it hollow down the middle, then each one, even if there's like maximal connection within each subgraph, it's always connecting less than half of the other vertices.
That's correct, but we should say it a little bit more clear. If I have 2 connections, there is a bigger one and a smaller one, or they're equal. The smaller one, how many vertices can have? If there's total n, how many vertices can I have in the smaller side? Maximum. n by 2. That's when they equal, if they're equal. If they're not equal, the smaller one has to be smaller than half, right? So in that smaller connection, how many edges can I have from a node? So if, how do I prove this? If G is disconnected, the smallest component has size, meaning number of vertices, at most n by 2. Because again, if there are two components, they can't be both bigger than n by 2. At least one has to be smaller than n by 2. So in that component, this is the small component. What's the maximum degree I can have from a vertex? If the whole thing is n by 2 and this is one of the vertices, yes, what's the maximum degree?
N minus 1. Or
Well, the maximum number of
n-
vertices
n
is
divided.
half.
Yeah.
So the max degree possible would be n by 2 minus 1, which doesn't satisfy my property here. Yes?
If it was two halves though, couldn't they just each have like no halves equal?
Right, but still, even if it's n by 2 exact,
Yes.
this is not a multigraph, doesn't have inner loops to itself. One node can only point to everybody except itself. So if it's n by 2, say 50 nodes in here, because I started with 100, I can only have 49 connections at most. Right? So that's easy, so that's connected. And here's what I'm going to do. Let's suppose I'm looking the maximum length path in G. So I'm done with that. G is connected. I already established that fact. G has to be connected. So this is done. The maximum length path, I don't know what it is, but I'm going to say, let's suppose it starts from a vertex x0 and it goes to x1, x2, all the way to xk. Let's say this maximum length, let's say it's k. I'm going to say this is a simple path. I'm not repeating vertices in it. So by path, I don't include the fact that I go through vertex x, I come back to x, and there's no cycles here, just a path. Of course, we want this k to be everybody and to show it's a cycle. That's our purpose, to show that we can find a cycle of size all the graph. That's a Hamiltonian cycle. But we don't know that's true. We started with this path. You see, let's see where it goes. So here it is. I'm going to draw it as a, this is, I can write it like that on the board or on paper. Or I can draw it as a line, x0, x1, x2, x3. Here's xk. Right? The maximum path I can find. Now, I hope it's clear that if I give you some graph, the maximum simple path, it's not necessary to include all vertices. Is that an obvious statement I'm making here? Because here's a graph. Do you think you can just find a path that includes all vertices without cycles, even if it's connected? That's not necessarily true, right? So the fact that this path does not include all vertices is not a trivial statement, right? So I want everybody to think a little bit mentally. If I just get a connected graph of some kind, any kind, what's the maximum path I could go? Right? Why there is a graph where there's no Hamiltonian cycle, even though it's connected? How can that look like? That I'm forced to, if I want to pass through vertices, I gotta go through a vertex twice. Like I think we already have an example, this UV here, right? That's like that. If I have, say, a bunch of nodes like this, say that's a simple, that's a tree, right? What's the maximum path in terms of length? 1, 2, 3. There is no way to find a path longer than 3 in here. even though I could have 100 vertices. So just somebody saying, here's 100 vertices connected, doesn't mean you can find a path of length 100. In fact, in here, the maximum path you can find is 3. Who's with me so far? This is an optional thing, like I said, even for honors. So don't feel like overwhelmed if it gets complicated. So the question of how long is the longest path is not a trivial question. It's not n necessarily. It could be 3, could be 4, could be 7, could be 11. We want to prove that in our graph, that's actually the whole thing. So now we have this path, and we know x0 has all neighbors, all its neighbors in the path. So I'm going to call this P is this path, maximum length path. So I'm saying if this path starts from x0 and is the maximum, somewhere in the list here must be all x0 connections, right? This is x0. x0 is connected to all kinds of nodes. And I'm saying it's not possible for some node z that's connected to x0 to not be in this path anywhere. That's impossible. Why is that?
Oh, I don't have an explanation, I have a question.
Let me explain this and then I'll get back to the question. So I'm saying a simple thing. If this is the maximum path you can get, it's not possible for x0, which is I have two ends of these paths, right? It's not possible for x0 to have some connection in the graph to some node z, and z to not be in here. Yes, why is that? Hmm?
If it's a Hamiltonian cycle, does not go through every vertex.
Right, but we don't know it's a Hamiltonian cycle yet. That's what we're gonna get. Yes.
Well, the graph is connected, right?
Yeah.
So all of the points that x connects to each other. So you
Yeah.
can follow them along.
But why is it that the maximum path must include all neighbors or connectors for x0? Which is, I'm not saying that's true for the middle ones. I'm saying it's true for the ends.
So even if like the maximum path is just like moving to one vertex, so let's just say that's the case, then all of x's neighbors are the maximum path and are therefore included. If there is a larger path, sorry.
Yeah, she's very close here, but again, we have to say
there's
it
a
right.
step more that I can't quite say, but.
Anybody else? I think you're very close. Again, what I'm saying is, this is the maximum path. If it's size 59, what the maximum size mean? There's no path in this graph longer than 59. That's what it says. Maximum means it's the longest path I can find. Longest means the number of edges, right? What it's saying is, then x0 must have all its connectors. Everybody who's adjacent to x0 in the graph must be in this path. You can't miss anyone. Yes?
If you don't use one of its neighbors,
Yeah?
then there's a bigger path that does use
How?
that neighbor.
He's saying if that would be the case, this is not the maximum path because I can find a longer one. How do you do that?
The one that actually uses all the neighbors.
So what do I do with that z neighbor to get a more longer path? Yes?
Start at the z neighbor.
Add the z here. If there will be such a z that's not in the list already, I could add z because it is a connector from x0, right? Z is a neighbor of x0. I add z and I just got a longer path. This directly contradicts the fact that the path I started was the longest in the graph.
So what if there's more than one node Z? It's not unfair.
I said simple path. I can't include a node twice. A simple
I'm
path.
saying what if there's multiple nodes that don't?
Then I get more. I get at least one longer path, right? Even if you're saying if there's a z1 and z2,
Yes.
if I add just one of them, I get a longer path,
Yeah.
which contradicts the fact that this was the longer path. Longer path, longest path means you can't have anything longer than that,
Yeah.
even by one. How do we feel about this? Hands up. Okay, we have to pause it for a second to make sure more hands go up, right? Question? You're good. So how this argument goes let me make a small parenthesis here. Do I think it's critical for you guys to know how to prove Dirac theorem? No. I do think it's critical for you to understand how complex reasoning goes, what are the steps, and how to think about it. This is just an example, and we can find more examples like this. So this step in here, which is the second step of the proof. The first step we already proved, G is connected. Second step of the proof. Pick the longest path, and we say, if this is the longest path, these guys, x0 and xk, the ends of the path, can't have any more edges connected that are not in the path. Because if they do, I can make the path even longer, which contradicts my longest path assumption. If it's the longest, cannot be made any longer.
So the neighbors that are like x1, x2, x3, they have to be connected to both x0 and x3.
No, this is just connected among them. x1 is connected to x1 and to x2, x2, x3. And this guy is connected to xk minus 1 and xk minus 2.
Because you said that.
But if there is a other connection that has not been used, some z connected to x0, that z must be somewhere in here. Because if it's not here, I could add it to the path and make it longer.
See that the two vertices at the end, they either have to be leaves, so that there's only one degree and one path you can go to, or the vertices are connected, are already used.
I'm saying the latest one, not the leaf cell. I'm saying what you said, the latest part. Every node that's connected to x0 or to xk, some other z, any such node that's connected to x0 and xk has to be in the path, has to be used, like she said. If it's not used, I add it, I make a longer path, and I keep going. The ends must have all their adjacency vertices used. Yes?
But what if you have, like, so what if the path, like, goes this way, right? And then you have two paths, like, just, so you have.
I can only use one path, like in here. Even though it branches this way, it branches this way, you can only go whatever's longest. A path is this, that. You can't, in a path, you can't say from here I go two ways.
Right.
A path is only one thing. Yes?
So just to clarify, you're saying not every vertex has to be used, right? It's just
No.
like a simple-
That's what I want to get to. Every vertex is used because then it's Hamiltonian. That's the end of the proof. Or for what I'm saying here, if you consider the maximum path, every neighbor of x0 and xk must be used. Yes?
So that statement is, that's only true when the degree x is greater than or equal to n over 2.
Correct. I'm proving that theorem. I know this. So I'm not doing any other case of graphs that do not satisfy this problem. Yes?
If you have to use every neighbor of the end vertices, does that mean the end vertices have to have a degree of 1?
No. This guy can be connected in the graph, not in the path. In the graph can be connected here, right? It could be an edge here, could be an edge here, could be an edge here.
Okay.
Those edges are not part of the path. The path is whatever I could find longest, obviously doesn't use all the edges of the graph or all the vertices. Like in here, right? The path may be from here to here to here to here, right? That's the path. It uses only 3 edges and 4 vertices, and there's a lot of other edges and vertices not used. What I'm saying, if this is the longest, it's not possible for this guy to have some other connection. Because I would add it, make a longer path. It's not possible for the ends of this path to have additional connections. If they do, I'll use them. Now it's possible that this is connected somewhere in the middle, because that one, it doesn't allow me to make the path longer. Yes?
So this statement is true for infinite graph, right?
Yes. But what property I'm saying in here, it's only true for the ends.
Yeah.
This is for x0 and xk. It doesn't apply in the middle, because if this guy has a connection, it doesn't mean I can make the path longer. How do we feel about this? Hands up, who's with me? Ah, yes. Yes.
Wait, so did you just say it works for every connected graph?
Every connected graph that has this property. Again, we're not proving any graph. We're saying graphs that have this property.
But that specific statement, that like if the max path must include
Oh yeah, that specific statement works for a graph. The maximum path cannot have additional edges, connectors for the ends, because if it does, you make the path longer.
Yeah.
That's some mental note worth making. Here's how I can attack some problem with the path lengths and such. Are we happy? Then remove. I mean, we gotta finish the proof. We have what, 45 minutes? Are we gonna? All right. This is not the hardest step in the proof. But so this, I hope we can slowly digest at it. I want to make clear this is an optional thing. You can choose to ignore it, not at home. You can choose to ignore it right now, and you'll be fine. But this is how real proofs go. It's something that the regular section will never do in the 4th series of study. Nobody in the regular section will see this proof. When they have to go to the master program to see this proof. Okay? Even then, it's questionable. PhD. You guys want to be in the other section, right? There you go. Okay, so let's keep going with the proof. Right? So what we established, x0 has all its neighbors in the path. Let's say y. Why we stating that? x0, the end, and also xk, of course, because they are the same, x0 and xk. They can have graph neighbors that are not in this path. If z is connected to x0, right, not in path, we just said, add z and makes path longer, which is a contradiction. Why is it a contradiction? Yes?
Because you're saying that the path you have now is the longest path.
Right. So if it's the longest, I can't make it any longer. Okay? That's why x0 and xk, the endpoints, must have all its neighbors somewhere in this list. Okay, so how does that look like? If x0 have all these neighbors in this list, here's maybe this is a neighbor, this is a neighbor, this is a neighbor, this is a neighbor, this is a neighbor. The neighbors of x0, these guys, let's call them z1, z2, z3, z4, so on and so forth. This is the neighbors of x0. They gotta be somewhere in here, in this path. We just said there's no neighbor that's missing. How many neighbors x0 has, at least? N over 2. So x0 must have n by 2 connections in this list. Now, of course, this is one of them, right? This x0 to x1, that must be a graph edge. But there must be a lot more edges here. Because x0 is a vertex in the graph, it must have at least n by 2 connections. So if n is 100, x0 must have at least 50 connections in here. And all of them, like we said earlier, are in the path. That is true for xk too. Xk is just another vertex in the graph. How many connections or edges it has? At least n by 2. So because there can't be any connection that's not in the path, all this is one of them, of course, but there must be a bunch of connectors in here, right? Those are graph edges. Those edges must exist because xk must be connected to at least n by 2 other nodes. And we just said, all its neighbors must be in the path. Xk cannot have some connector outside this path. Hands up, who's with me? Oh, we're doing very good here. No, I really mean very good. I don't just mean to be nice. I tried this proof with my PhD students last week, and they didn't do that good. So you guys are doing great. So I have n by 2 connections coming from x0, and n by 2 connections coming from xk. Those are graph edges. My point is, they have to hop over each other. The last connection from x0 and the first connection from xk, they have to be, this one jumps over this one. If we look at this particular point, which is, where is the earliest connection xk has in the path. And where is the latest? Let's say latest from x0. And this is earliest xk. This is the first hit xk has. It doesn't connect any further. So there's n by 2 hits in here, at least, because xk has to hit n by 2 neighbors. And there is n by 2 hits from x0, the last one being whatever, somewhere. Those 2 points, this one must be after this one. Because the length of this path, it's at most
100.
n, 100. And if this one has to go back to at least 50 places, that are not even one after the other, maybe jumps few, so it might go even earlier than 50. And this one has to go at least 50 places forward, even jump over some of them. This stuff has to be more to the right than this x here. Yes.
Could it also be the same vertex? The earliest would be-
I don't think it can, because if you don't have, if you have n, if you do a little algebraic calculation, if you get n by 2 back and n by 2 forward, excluding the 2, then you gotta go over. Because if I can go n by 2, and then from that one, like you say, n by 2, then I think the total gotta be n plus 1, but there's no n plus 1 vertices. Right? So that's a little, it's a good question. Can possibly be the same one, the last one that's connected? I don't think it can. I think n by 2 and n by 2, they really have to jump over each other. That's the only way. Because it's n by 2 other than itself. So it's that one, n by 2 connection, and then n by 2 connection, that one, plus the n. So I think there's too many to not cross over. Hands up, who's with me? Let's call this earliest one here, let's call it xi. And let's call this one xi plus 1. Or some xj or something. So how do we say that? x0 has n by 2 neighbors in path P going to the latest, we say xi plus 1, this one, and xk has n by 2 or more neighbors in path P going to earliest xi here. I'm skipping some detail here, whether xi and x, can I find, if I have all these dense connections and dense connections from here, can I find two, not just that overlap, like I said, that's after that, but they're next to each other? That's an interesting question. Can I find two that are actually next to each other? And I'm going to need that, but I'm going to skip that detail, something that can be figured out. I want to finish the proof, that's why. So now we say, here's a cycle, x0 jumps to xi plus 1, so it jumps here. I'm reading it from here, x0 start to the last one, xi plus 1. Then it continues to the path. This is the path, P. So it's really xi plus 2 all the way to xk. So this was a jump here. Let's go, it's very nice. Jumps here. Then it continues in this path from xi plus 1. It goes straight to xk. From xk, it jumps to xi. And from xi, it goes back in the path to x0. Jumps over, finish to xk. From xk, uses this connection to go to xi. And from here, it goes back in the path, back to x0. Is that a cycle? x0 goes to xi plus 1, goes all the way to xk, jumps back, comes in here. Is that a cycle? cycle, right? I say this is Hamiltonian cycle.
How do you prove the xi plus 1 is after?
I just said that. We need a little detail in there to see what that happens. Maybe we leave that as a homework as opposed to the whole proof. Why is it xi plus 1, not just after xi, but it's right after xi? Why is that possible? So my biggest problem now is I found the cycle, but why is it Hamiltonian? What does it mean to be Hamiltonian? Have to include all vertices, right? Once it's fine, it was simple at all times. I never use a vertex twice, so I'm not worried about repeating vertices. The question is, can I miss something? Right? So I found a cycle, great. It's not complicated cycle with repeated vertices. I don't have to worry about that. But what I really want to say, this cycle actually passes through all vertices. So what's the alternative? If that is not true, then what? How can that not be true? Not pass through all vertices? Yes? There's some vertex not in it.
Yeah.
Huh. Let's say here's my favorite vertex Z, not in it. Remember that the graph is connected?
Yes.
So Z must be connected to these guys somehow. Not directly, necessarily, right? But it has to be maybe 1H, 2H, 3H, 4H, 5H. At some point, it goes in here somewhere. Right? If there is such a Z, it has got to be a connection to these guys, to this group. But if there is such a Z, I can just take Z, the one that's right connected to the it, right? I mean, instead of going a Z that's far away, it requires a lot of edges to connect in here. I could just say, just walk from this path and pick the Z that has a direct edge to the path. Right? So the fact that it's connected, it means there is some guy that's immediately connected. Do we follow that statement? So the fact that there's some Z outside, there's got to be a path. So you walk on that path until you're about to hit my group here, my cycle. And the last guy before hitting, that's directly connected to the cycle. So if there exists Z not in this cycle, then you walk up this path due to connectivity of the graph, right? Connectivity. There is a connection Z to the path, to the, say, exactly to some X, one of these X's, let's call that X, where it hits X, I don't know, X T. So there's a connection XT. Again, how did I do that? I say, there's a Z outside the path, fine, then it's gotta be connected somehow. So I pick a point that's in here, just connected with a branch to this XT. Why is this a contradiction? Why this cannot happen? Yes?
Because the math's length was like all,
I could do the same trick before, increase the length of this. I could find a longer path. If this is true, if I read those vertices, all of them, in a particular order, I would get a longer path than the one I started with. But I have to be careful in what order I read them. I can't start from x0, because x0, x1, da 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 da. I got this connection extra in xt in here, right? This is my connection to this z that's not in the path. But if I go from x0 to here and to z, I'm not increasing the path, right? How can I use this z to increase my path? I just have to read it in a different order. Yes?
You start at z.
Start at z,
And then go
to xt, and then
through the cycle.
follow the cycle. Cycle can be read in any order, right? So the cycle is of size k. So anywhere I read it in whatever order, I get k. So if I go from z to here and read this cycle, I get k plus 1. Who's with me on that? That's it, we're done. See? Not bad. PhD level proof. Yes.
Is that proof for why that z can be added the same proof as for why you can say that there's an xi that connects to xo and an x?
No. You guys need a little bit of how those density goes together so xi and xi plus 1 are next to each other. It's not a hard thing. Just you gotta be drawing a big paper and make sure you see how it goes. Yes, he was with the hands up before you.
I was able to follow that, but there's no way I could write that out. Like,
Let's not put it in the exam then. I can promise you this will not be in your exam. They say it's optional. Did I also say your exam is the same as the regular section? How do you think they would feel about it? Yes.
Okay, so I understood the last part with the z, how you just...
If there is a z that's not in this cycle, it's connected somehow to the cycle.
So you just start from here.
I start from z and then follow the cycle.
Right, but yeah, but then how, as a cycle, you have to get back.
The cycle allows me to read these vertices in a certain order, but from wherever I started. Just the fact that it's a cycle, on a cycle, I have it drawn here. On any cycle, I can start wherever I want and go through all vertices.
And then go back.
I don't have to go back
Oh, you don't have to.
in this because I just want to increase the path, but I can start from here and go through all of them. I can start from here, go through all of them. I can start from here, go through all of them.
Okay, so if you drew like an extra line, an extra edge from the pentagon to your head,
I could start here at Z, go here, and then go through the rest.
and then go back, and that's so considered.
I don't need to go back, I just increase the path length. If I go through here from here and then that, I've increased the path length.
I think the idea is that if it's for the cycle and you only use the vertice once, it'll probably make it.
But my only proof for contradiction is that increases this path. I get a longer path if I can add a Z to it. That's my point. And that's not possible. You have to count carefully. I think that's the same problem she has. Count carefully the number of edges. But you'll see that just adding one vertex, if you can add it, and you still have a simple path, it will be one extra edge. Because whenever you read this path, you're going to get k edges.
Sure.
If you add one edge, it's a longer path. Yes. I can't hear you. We said that. Is it possible to get n by 2 connections this way and n by 2 connections that way, and then the earliest connection to xk to not be before the latest connection of xi plus 1? The reason this is not possible, anybody can answer this question, why this guy has to be before this guy?
Is it because if it was like that, that would mean there would be a bridge?
No, the argument was different. What was the argument? Why is it that this first connection or earliest connection of xk is on the left side or the latest connection to xi plus 1?
Well, isn't it because it can only connect to like n over 2 minus 1 because it can only connect to one that's other than itself, so it wouldn't be n over 2 connections.
Correct. It's said backwards, but that's what she means is correct. If you have n by 2 connections going back from xk and n by 2 connection going forward, they must overlap because there's only less than n nodes. The way she said it, if you wouldn't have the overlap, you can't possibly have n by 2 connections and then after n by 2 connections and still have only n nodes. How are we feeling about honor section now? Feeling better? Let's see what else we can do today. That, by the way, is not the strongest result on Hamiltonian path. This has been proved about 1960, and since then, there are stronger theorems. By stronger theorems, they do imply Hamiltonian paths, but they make weaker assumptions. So they use a weaker hypothesis. This is quite a strong assumption. Everyone has to be connected with half of the graph. They prove later that you can actually use less and still prove there is a Hamiltonian path. But the less you use, the harder the proof goes, right? Because you have less to work with. All right. So here's what I would like to do next. I would like to introduce you to a huge area of computer science for graphs. which is the shortest paths area. Now, if we don't have weights on the edges like so far, remember recitation with us, the shortest path question between here and here? What does it mean, shortest path? What? Minimum number of edges. So how do you get from here to here in fewest number of steps? However, now we're going to complicate things. We're going to say we have graph with weighted edges. That's we call weighted graph. So here's one. This one is directed, but it doesn't have to be directed. Again, directed, undirected, it applies to weighted or unweighted. The difference in this kind of graphs, so directed allows me, even if it's a simple graph, this is not a multi-graph, I can have edges now both ways, right? Because I don't say I have multiple edges. It's not a multi-graph like in Königsberg problem. I'm just saying there is an edge this way and an edge this way. Some people found it easier to think about this like a pipe water system or electrical system or network that says on this pipe water flows this way and on this pipe water flows that way. Or one-way streets. There is a street from here to here, one way this way, and there's another street that way. You can think about this with a physical analogy. I actually use a physical analogy all the time with the graphs. Either cities with roads or water systems or network systems, whatever I think is appropriate for that problem. So here's the node, another node, and I have the difference in here. I have weights. So here's 10, 5, 1, 2, 3, and 4. And we can call these nodes, say, I'm going to call this one S, this one X, this one Y, and this one. I want to leave some space under it to write something else later. I'm going to put this Z here. So one question, there are three questions of shortest path that are major questions. I'm going to list them and give you a hint of kind of how do you go by doing that. So one important question, we call it Q1, it's I want the shortest path from some node S to everywhere. I don't think I have to say how important this problem is in practice. I bet any one of you can come up with life and death critical examples. Things like Uber would not even exist if this problem cannot be solved, right? With Google Maps, you name it, distribution systems, food production, you name it, everything at some point has to do, I'm here. What's the fastest way to go everywhere I want to go? Airplane flights, network distributions. There's so many problems about this. I have a general starting source distribution point, whether it's food or whether it's electricity or whether it's water or I don't know, anything, even conceptual stuff like how knowledge propagates through academic papers. There is a source and then how does it distribute? Same exact problem, right? And these edges corresponds to a lot of physical properties. Could be capacity of the pipe, could be the distance, could be the cost to send food that way, could be the, I don't know, gas consumption. Could be a lot of things on those weights. So this question pops up very naturally in a lot of places. How do I find the distances, the shortest path from source, from wherever my truck is now, to everywhere? Do you have an answer or a question?
Question, and depending on how that goes, maybe an answer. What do you mean by everywhere?
To all the other nodes.
All the other nodes, okay.
So of course, if the graph is not connected, there's no, if there's a node that the source is not connected to it, I can't get there, the distance or it'll be infinite, because I can't go to that place. I'm not talking about that issue right now. Yes?
Would it be the path with the smallest sum of weights?
Right. That's what I mean by shortest path in a weighted graph. This is the path with the smallest sum of weights. That's exactly what I mean. This is different than the paths we have so far. When there was no weights, we thought just figure out how many edges are there. So the shortest path was the one with the fewest edges. Now that corresponds to the same notion if I consider every edge with weight. If I say in an undirected, unweighted graph, every edge has weight 1, the shortest path by weight comes down to the smallest number of edges. Are we agreeing on that?
Yes.
Are we guys sure?
Yes.
If I say every edge has a weight 1, smallest path is the fewest numbers of edges. Right, so the question is, how do you find such a thing? Now, programmatically, like write a program, given a graph with weights, with everything, how do you find the shortest paths from S to everywhere? Question or answer?
I have an answer.
You know how to do this?
Well, I guess what you could do is you could start with a node that your start node and then wherever you're trying to get to.
So the distance, I'm going to say estimate, the distance to this node is 0, because that's what I started. Right?
And then where you're trying to get to, and then you could expand.
So what will be the distance here?
The distance from S to X.
Will be 10.
10.
Right? So currently the distance will be here. So I'm in S. I'm kind of trying to go from S. But this may not be the smallest distance. It's just the distance I could find so far on this edge. If I go through this edge, it's 10. But it may be that not going through that edge is smaller. In fact, it is, right? 5 plus 4 will be a better path. That's the difficulty here. Going through a direct edge is not necessarily the fastest way. Because if it'd be a piece of cake, right? So how do we go by efficiently with a computer program, with an algorithm, to find the paths? Yes, all the way back.
There's the nearest neighbor algorithm. I think that's what it's called.
There is that. I don't think it solves this particular problem. But nearest neighbor is a very interesting thing to do, just not solving this.
Maybe you could do something like a breadth first search, where you just expand out all the paths and then measure the shortest one. And then
I like the word something like.
Well,
Because to some degree, everything is something like what he said, right? Like if I say right now, the answer to this question is Dijkstra algorithm. Who's to say Dijkstra is not like what you say, BFS? Maybe it's like, I mean, it does graphs and all that. So I think you're about right. BFS, which we don't have to worry about it today or tomorrow, is a way to traverse the graph. So he wants to traverse this graph in a way that updates those paths. That's the right idea, but it's not BFS. So here's how we're going to do this. And we don't have to actually do it. We're going to study this in the algorithms class, how to write a program, analyze it, and do that. But the idea is this. I write out these estimates, 10. I'm still in S. If I go this way, what's my estimate to here? 5. It's still an estimate. But at some point when I'm done, I'm going to declare magically, I need some math to do that, that some of these estimates are actually the smallest value. For most of them, I don't know if it's the smallest or not. This 10, I don't know if it's the smallest. But the smallest one of them, the 5, I can have a theorem that says, if you pass through all the edges, the smallest one of your estimates is actually the minimum path. That's a nice theorem to have, because with this theorem, I can write a much better algorithm than going through everywhere. So if I know this 5 is actually the smallest, is it? Yes. If this is 0, because that's what I started, I pass through these edges, and I get this 5. 5 is actually, I can count on the 5 as being correct. I cannot count on the 10. Why? It's not the smallest. I can only count on the smallest value. Then where should I move from S? I move to the 5. The one that I know the distance from S to that is guaranteed to be 5. It cannot be smaller than 5. Again, I can promise that guarantee only for one node, which is the smallest. So I move to this 5, and I go from the edges from the 5. What would be the distance here? If it's 5 to here and 1 on this edge, what's my estimate here? 6. If I go 5 plus 4, what's my estimate here? 9 is better or worse than 10? Better, right? So I cut the 10, I put a 9. and then I'm done from the 5, and again I'm like, which one is the smallest, which I can guarantee mathematically it's actually the smallest, because the other ones I can't. I can do this one, right, 6. So then I'm in here, and I'm saying, okay, here, past this edge, 6 plus 2, 8. That's even better than the 9, so make it 8. If I do this carefully, I actually get the distances from S everywhere, quite efficiently. It's not one of these trial possibilities, takes forever because there's too many cycles like the other one. This could be efficient with one condition. Weights have to be positive. If you didn't think this is complicated enough, there is a version with weights can be negative. But if weights are possibilities, we're going to do Dijkstra algorithm. That's the one I just described. Dijkstra algorithm goes efficiently to these points if the edges are positive and figures out exactly this, shortest paths from some point, the starting point, which you have to indicate, to everywhere else. And it does exactly this. It goes through those points, puts an estimate. Every time it finds a better route, changes the estimate. And the only estimate that's guaranteed to be the actual correct number is the smallest one. So when it goes further, when it advances, it can only advance to that point where it's guaranteed to have the minimum. See, the problem is, if I advance here from S, from here I cannot measure anything because I don't know if this 10 is correct.
What if there were 2 edges coming out of S that both had weight of 5?
I'll have 5 here, 5 here.
Okay.
And
So
then,
guaranteed for both.
yeah, will work out fine. I can pick any one of them to advance from there. But it won't work for negative weights. So for negative weights, there's something more complicated that's not that efficient. So that's one problem with shortest paths. Here's another problem with shortest paths. Problem number 2. It's called minimum spanning tree. I have a graph here, a different graph. This is undirected, but has weights, of course, because we now deal with weights. So how is this connected? This way, this way, this way. There's a connection here, here. I think it's done. See? Triangle. Okay. So weights are in here 4, 8, 11, 8, 7, 9, 14, 10, 2, 1, 7, 6, 2. Those are the edge weights. The minimum spanning tree problem is find a connecting, meaning all vertices, tree. So don't use all the edges. I don't want all the edges. I want just some of them that form a tree, the connecting tree, the spanning tree, with total minimum weight. Minimum. So I want a tree that connects everything. Obviously there is some tree connections in here, like not use all the edges, such that the total weight of the tree is minimum. Question or answer?
I think you're missing a weight on one of the edges there.
This one?
Yeah.
This one is a 4. So what would be the minimum spanning tree? That is a spanning tree. How many vertices are here? How many vertices? So if I want a tree with those vertices, how many edges it must have? 8. So any spanning tree will have 8 edges. That's guaranteed. The problem is there's more than one tree that can connect, use some of these vertices and connect everything, right? I want that tree which is the smallest total weight. Again, I hope I don't have to say why this problem is important. In any distribution, different distribution network, I may have to know what roads I need to use. I don't need loops or cycles because everything connects to the highway and the highway goes to Boston, right? But then I need a tree that allows the minimum distribution, right? Actually, water is distributed this way in a tree. There's a big pipe coming in your town that distributes to neighborhoods, and each neighborhood distributes to streets, and each street distributes to houses. It's not a loop on water pipes, right? It keeps going down a tree. And we want to find the minimum weight tree to not send too much water to those pipes. If you pay attention to the news yesterday, somebody puts too much pressure in a gas pipe, and a bunch of houses in north area of Boston, about 100 houses were on fire. Distribution networks are a critical point in infrastructure of every city and county and so on and so forth, not just in here. China or Europe, the same problem. What's the minimum spanning tree here? How do I know what edges are part of that tree and what edges are not? Of course, I need how many edges again? 8 edges. So do you think 14 will be part of that tree? Why not? It's too big. How about this one? That looks good. 1. What else looks good? The 2's. Here's a 2, and here's another 2, right? I don't have a 3 yet, but I'm working on it. What else looks good in here to make a connecting tree that's kind of, I have to get to 8 edges, right? That I cannot avoid 8 edges, because to get a tree connecting everybody, I must have 8 edges. Who's with me? Hands up. Trees, b minus 1 edges. That's unavoidable. So what else looks good in here? 4. Here's a 4 that I could use. And here's another 4, right? Can I use this 4? Yeah. What else looks good in this tree? 6 looks like an interesting small number. There's a problem with it. What's the problem? It forms a cycle, so it can't possibly add it to the tree. If I want to add 6, I have to take something out. If I keep the blue edges that I already have and I'm trying to add the 6, that's a clear violation. So should I put 6 in and take some edge out? No. Why not? Because the edges I just put in are smaller than 6. So if you swap 6 for another edge that's smaller, you're actually not going to get the best tree. So we can't use 6. I'm going to make it red. What else do we can use without creating cycles? Can I use this 7?
No.
No, but can I use this 7? Okay, how about 8? Can I use 8? This 8? How about this 8? I can use either one of them.
But you can't use both.
Why not? It'll be a cycle. So take your pick. You like this one? No. This one. Take your pick. Am I done? How do I know I'm not done? I need v minus 1 edges. I can't be done with more or less than v minus 1 edges. So how many edges I have? 1, 2, 3, 4, 5, 6, 7? Which vertex is not connected yet? So which one I use? 9. That's another algorithm you guys are going to study in algorithms class. There's actually 2 ways to do this. Exactly this I can achieve in 2 ways. I can do it the way I did it. That's called cruise color. But I could do a slight variation to only use edges that are connecting to my growing tree. So the way I build it here, I have many disconnected parts, and I add in an edge, and every time I add an edge, I'm actually connecting 2 parts together. The other way I could do this is to start with a minimum edge. It only adds to that edge. So if I start with this edge, I can only go from here. I have now those 2 connected. Which edge can I use to increase? I use this edge. But now remember, I can only go by the connectivity. I have this edge. What edge can I use that connects to this and this, the smallest edge? The 4. And now I have those connected. Which one do I use? 2. Now I have all these 4 connected. What else can I use? These 7, right? So it gets the same answer, but it connects, it only uses one tree, it just grows that tree, as opposed to the first version, which was just adding edges everywhere, not creating cycles. This is called prim. Either way, those algorithms are very efficient because they go very greedily, pick the next good edge, go on with it. So this could be implemented very efficiently. Finding the minimum spanning tree, that is the tree that connects all vertices and has the minimum total weight. I have a question for you guys for next time. Do the algorithms, these algorithms work for negative weights? We already said that one doesn't work. If you want to impress me, you show me why that algorithm does not work for negative edges. But you can also impress me by saying, Kruskal or Prim, this mechanism creates spanning trees this way. Can I use it if the edges are negative or not? Would I get the minimum spanning tree, including the negative weights? So that's a question for next time, because I have one more shortest path problem to show you. That is the traveling salesman. You know this one? Yes. This one says, it's a graph. Let's do a smaller version because we're running out of time here. Here's this graph. And has weights, of course, 20, 34, 35, 30, 42, and 12. So it had these weights. Now, the minimum spanning tree will include what edges? How many vertices here? 4. How many edges would I need to get a spanning tree? 3. What will be the 3 edges that I should use to connect everybody? The 12, the 20, and the 30. Those would be the 3 smallest edges that I could get a tree out of them. Fine. Now this is not that. This is saying, find me a Hamiltonian cycle. What was that? Hamiltonian cycle, again? Cycle that passes exactly once through over. So pass exact once through each vertex. That is the Hamiltonian cycle. That alone is difficult, right? We just said we don't know how to prove that in general, and it's hard to find. The only general solution we have for that is to trial all the cycles and check if there is a Hamiltonian one. Very expensive computer algorithm. But this one is even worse. It says of minimum total weight. It's not just one Hamiltonian cycle, because there could be easily more than one. In a dense graph with a lot of edges, you can have multiple ways to go through these vertices, right? Just find me the one with the smallest weight. So one thing should be clear. If it was hard to find a Hamiltonian cycle of any kind, cannot be easier to find a particular Hamiltonian cycle, right? I mean, think about common sense logic. If this would be an easy problem, how can I solve the first problem of today's lecture? I just put some weights, 1, 1, 1, 1, 1 on every edge, right? To just have some weights. Call this problem. That's easy, presumably. Find a Hamiltonian cycle, the minimum weight. Isn't that a Hamiltonian cycle? It is, so I would have solved the other problem. If that problem is hard, this one must be harder. There's no way to say that's hard, but there's a very simple solution to this problem, because this problem could easily solve the first one. That's what I just said, this mechanism, hard problems implies this other problem. It's a very important mechanism in complexity theory. You're going to have a class, some of you, that's called theory of computation. That whole class is based on this idea. If this problem is hard and it can be used to solve another problem, right? That problem, it's as hard as this one. You can't use an easy problem to solve a hard problem. So this is a hard problem with enormous implications through atmosphere analysis, astrology, geography, cartography, microchip design, DNA sequencing. This TSP problem, like most of you heard, extremely hard. So how do we solve it in general? What's our only way to solve these problems in general? Brute force. Try all cycles and see which one's the minimum. Now, in particular graphs, there are good solutions. If the graph is acyclic, if the graph has few edges, if the graph has certain structure, there is all kinds of ways for those graphs to do it faster. But in general, it's just a hard problem. We don't have a good solution other than trying everything and see what we get. We're done with graphs. If you ever encounter a set problem that you don't know what it's about, please use Google. Right? Like, what's Cartesian product? I don't know. Well, you can wait until Tuesday. If you don't know how to use Google, you can wait until Tuesday and I'll tell you.
Do you have any more classes today?
I don't know. I know how to computer, I know what it is. I think it's far away. My publications are not ready. But I published with somebody. No, wait. I published somebody who has even 4, so mine is 500. But mine is not relevant in fields that are not related to it. I mean, that's interesting for me. This story. AI, what I do. Stochastic gradient descent, very good. It's up to you. I didn't do it. You guys have a reputation that's like 5 times bigger than the system. So if you did a first two pages, it's wrong. Let me close the camera and then I can answer. Sure. Yep.
Well, I have to leave too.